This section explains why the whole shape of the cosmos reduces to a single function of time. Start by assuming the universe looks the same everywhere and in every direction, homogeneous and isotropic. Once you assume that, geometry stops being free. Weinberg's opening move is to show that this symmetry alone forces the Robertson-Walker metric almost uniquely. It leaves three candidate spaces, flat, spherical, and hyperspherical, each carrying a single curvature constant, and all of them stretched by one time-dependent scale factor, written A of TT embers, walks Orkin A of T. The entire kinematics of the cosmos collapses into that one function. Feed the metric to Einstein's equations, and A of t acquires its equation of motion. Everything you can observe becomes a readout of t and its derivatives, the redshift, the luminosity, and angular distances, the Hubble constant, the ages, and the Hubble constant, the ages, and the Hubble constant, the ages, and the horizons. This chapter is the book's spine. Symmetry becomes geometry. Geometry becomes one scalar, and every later chapter perturbs around it. This section explains how one symmetry assumption fixes the entire stage of modern cosmology. Assume the universe looks the same in every direction, to every freely falling galaxy. Isotropy plus no privileged vantage forces homogeneity, and the geometry collapses to a single form, the Robertson-Walker metric, with one time-dependent scale factor, a of t carrying all the remaining freedom. That is the chapter's whole move. A symmetry assumption fixes the stage, and everything observable becomes a reading of t. Redshift measures how much A has grown since emission. The distance ladders calibrate its present rate. The field equations in section 1.5 turn matter content into the evolution of t, whose late time acceleration of t, whose late time acceleration betrays vacuum energy. Chapter 1 stays in the recent universe, at redshift less than 10, the epoch of galaxies. The cost is this: the principle is assumed, then checked against the sky, never derived. This section explains how the geometry of the cosmos is fixed by a symmetry demand before any physics of matter or gravity enters. Demand that space look the same everywhere and in every direction, and you have already written down the metric before any physics of matter or gravity enters. That single symmetry demand collapses the infinity of possible three geometries to exactly three constant curvature options: flat spherical with k equal to +1 and hyperbolic with k equal to +1. Time enters only as a scalar dilation, the Robertson-Walker scale factor A of t, multiplying that frozen spatial shape. So the cosmos is not a general spacetime, but a one-function family. Pick k, pick A of t, done. Everything downstream is bookkeeping on this constrained form. Redshift, momentum decaying is 1 over A, densities decaying is a 2 the power minus 3 times 1 plus W. The chapter's move is that symmetry fixes form. The geometry is legislated by isotropy, not fitted to observation. This section explains the cosmological redshift, why a photon's stretch measures the growth of the universe itself. A photon carries no ruler. It measures the universe only by riding it. Between its emission at time t1 and its reception at time t0, its wavelength stretches by exactly the factor that the scale factor grew. 1 plus z equals A of t0 divided by A of t1. That single ratio is the redshift. No velocity and no distance traversed enter it. The familiar Doppler reading, galaxies fleeing at c times z, is a crutch, and it snaps precisely here. The stretch depends not on how fast it changes at either endpoint, but on the total expansion during the light's whole flight. Read z, and you have read the ratio of two epoch sizes, the wave, a clepsydra, timing, the cosmos's growth. This section explains why cosmic distance has to be built as a ladder. Nothing far enough to reveal cosmic expansion is near enough to measure geometrically, so distance is built as a ladder, each rung a standard candle, calibrated by the shorter rung beneath it. Parallax triangulates the nearest stars. Those fix main sequence and Cepheid luminosities. Cepheids, in turn, calibrate whole galaxy relations, the Tully-Fisher relation and the fundamental plane, along with Type 1, a supernovae, which finally reach distances where recession velocity swamps local motion. Only there does velocity over distance stability swamps local motion. Only there does velocity over distance stabilize the way. The primitive is bootstrap metrology. No single method spans the range, so absolute calibration propagates outward from geometry, and error compounds with it. The Hubble constant is never read directly off the sky. It is the top of a tower, as uncertain as its shakiest rung. This section explains why a single number stops describing distance once space itself expands. Distance stops being a single number once space expands. Fix a source. Two observables measure it differently. Its flux defines the luminosity distance. Its angular size defines the angular diameter distance. Each is only the proper distance dressed by the photon's redshift history, so they cannot agree the luminosity distance equals 1 plus z squared times the angular diameter distance. It's quas 1 plus z and dest. One factor of 1 plus z drains each photon's energy. Another factor stretches their arrival in time. Angular size pays neither tax. The maxim is operational. A distance is whatever the measurement demands, and the expansion factor is pure bookkeeping between channels. Weinberg, then Taylor, expands the luminosity distance as a function of redshift. The coefficients past Hubble carry names, deceleration, jerk, snap, the higher derivatives of the scale factor made observable. This section explains the dynamics of cosmic expansion. Everything before this was geometry, true for any expansion, whatever fills it. Dynamics enters when Einstein's equations meet the Robertson-Walker metric, and out falls a single relation. The square of A dot plus K equals 8 pi g over 3 times rho times A squared. Its structural surprise is that Birkhoff's theorem lets you rederive it from Newton alone. Take a co-moving ball, hold its kinetic plus potential energy constant, and the spatial curvature, k, stands unmasked as nothing but the total mechanical energy. So curvature is an escape velocity ledger. K equal to 0 or minus 1 unbinds the ball, it expands forever. K equal to plus 1 is bound, it halts and recollapses. The fate of the universe reads off the sign of an energy. This section explains what you learn by pushing the distance redshift relation past its linear term. Push that relation past the linear term, and you are reading the second derivative of the scale factor. Hubble's law is only the first Taylor coefficient, h0. The curvature of the plot at large redshift is the second coefficient, the deceleration parameter q0. Standard candles, meaning type Ia supernovae, at high redshift fix both of these at once. The reversal is this. The supernovae arrive fainter and therefore farther than any decelerating universe permits, so Q0 is negative. Expansion accelerates, which forces a negative pressure component into the energy budget. The whole section is one move. Take the luminosity distance as a function of redshift and Taylor. Expand it, and each successive coefficient buys one more time. Derivative of cosmic geometry. The sign of the second one is what broke the matter. Only model. This section explains how to tell cosmic expansion apart from tired light when both produce the same redshift. Redshift alone cannot tell an expanding universe from a static one where photons merely tire and bleed energy en route. The frequency shift is degenerate between them, meaning the two accounts predict the same shift. What breaks the degeneracy is the character of expansion. Expansion acts as a global time dilation, reaching beyond a simple photon energy loss. It slows every rate at the source by a factor of 1 plus z, while tired light slows no rate at all. So you stop measuring the shift and measure a rate instead. Two rate measurements carry the signature. Surface brightness, once you fold in the angular geometry, must fall as 1 plus z to the power minus 4 under expansion, but only as 1 plus z to the power minus 1 if the universe is static. This is Tolman's test, and a distant supernova's light curve must stretch in time by a factor of 1 plus z. Both effects are observed. The primitive is this: to separate two accounts of one shift, find the second independent power of 1 plus z that only one of them imprints. This section explains how the age of the universe gets a second independent check beyond the expansion model itself. The expansion model hands you one number for the age of the universe. Feed it h0, omega matter, and omega lambda, then integrate. This section refuses to trust that number on its own terms. Instead, it dates the container by dating its contents. The cosmos cannot be younger than the oldest thing inside it. Two independent clocks supply the floor. The first is radioactive decay ratios, the R-process nuclei, uranium-235 measured against uranium-238. The second is the main sequence turn-off of the metal, poor population 2 stars in globular clusters. The move works as a consistency constraint. It adds no fresh measurement of its own. Instead, two unrelated physics, nuclear decay rates and stellar evolution, must agree with cosmic geometry. Convergence is the whole point. A floor above the model's age would break the theory. This section explains how radioactive isotopes act as clocks that place a floor on the age of the universe. A radioactive isotope with a known birth abundance and decay rate is a clock. Read how far it has depleted and you recover the elapsed time. Figure 1.5 applies this to the ancient star BD plus 17 degrees 3248. Its thorium and uranium, forged in a single R-process burst, now sit below the initial abundances. The solar system pattern predicts, and that deficit reads 13.8 billion years. The universe must be at least as old as the oldest thing inside it. A clock ticking within cosmology bounds. Cosmology from below. This is carbon-14 dating pushed to isotopes slow enough for cosmic time. The chapter's move is to pin the age, not by modeling expansion, but by finding independent internal clocks, radioactive decay, here, main sequence. Turn off next, that must agree. This section explains how a single symmetry assumption collapses all of cosmology onto one function of time. Assume the universe looks the same at every place and in every direction, homogeneous and isotropic, and the geometry has almost no freedom left. That single symmetry postulate, the cosmological principle, collapses the whole space of possible space-time metrics onto one family, the Robertson-Walker form, fixed up to a single scale function, a of t and a discrete curvature sign. Friedmann reached it by solving Einstein's equations. Robertson and Walker showed that symmetry alone forces it, no dynamics required. That is the chapter's generative move. Symmetry, not the field equations, does the constraining, so cosmic expansion reduces to the behavior of one function of time. Everything downstream, from redshift through dynamics, is bookkeeping on redshift through dynamics, is bookkeeping on a of t. This section explains how mass gets measured in the universe when what we want to weigh gives off no light. Gravity is the only instrument that weighs what does not shine, so mass here is read from motion, never from light. For a bound system that has stopped evolving, a system we call virialized, the virial theorem clamps twice the kinetic energy against the potential, so the measured spread of galaxy velocities inside a cluster fixes its total gravitating mass, without asking what emits. Weinberg's chain runs like this. First, virial weigh the clusters, then divide by luminosity to get a mass-to-light ratio. Then, assuming clusters are typical, multiply by the whole sky's light to reach omega m, the matter density parameter. The surprise Zwicky first met here is that dynamical mass towers over luminous mass, and the entire estimate rides on that one ratio being universal. This section explains how a redshifting sightline becomes a detector for the gas that lies between us and a distant source. A redshifting sightline is an integrating detector. As the source's light travels, it continuously loses frequency, so it inevitably sweeps through the resonant line of whatever atoms lie along the path. Each cloud it crosses subtracts photons, and the observed dimming integrates the whole intervening column. Here is the decisive fact. Resonant Lyman alpha absorption has a cross-section so vast that even a trace-neutral hydrogen fraction saturates the ray into a black trough. This is the Gunn-Peterson effect. That extreme sensitivity inverts the logic of a null observation. Seeing no trough toward quasars, out to a redshift of about 5 sets, a tight upper bound on neutral hydrogen, evidence that the medium was already ionized. And the trough's onset at higher redshift would date reionization itself. This section explains number counts, how tallying sources by their apparent faintness reads back the geometry, the light crossed to reach you. Faintness proxies distance. In flat, static space, the volume enclosing sources within reach of a given brightness grows as the cube of that reach, while flux dims as the inverse square of distance, so the number of sources brighter than a flux L scales as L to the -3/2. Here is the essential surprise. That exponent is fixed independently of what the sources are. Whatever the spread of true luminosities, it washes out into a single geometric slope. So -3/2 is the null hypothesis of a Euclidean, unchanging cosmos. Every deviation is signal. Spatial curvature, expansion, and the evolution of sources with cosmic time each bend the count law, and the bend is what you measure. This part explains how quintessence replaces a fine-tuned constant with a field that tunes itself. The move of section 1.12 is this. The dark energy driving cosmic acceleration need not be a rigid vacuum constant, the cosmological constant, capital lambda. Let it instead be a scalar field, phi, rolling down a power law. Potential, a potential proportional to phi raised to the negative alpha power. The payoff is the tracker solution. an attractor onto which the energy density of phi settles, regardless of where it started. Late time acceleration then demands no delicate initial value. This is the attractor move. The dynamics forget the initial data and select the endpoint, converting fine-tuning into near inevitability. One clarification on the concept title. The steady-state model named alongside quintessence is a separate historical rival from section 1.5. It was abandoned because of the microwave background, not because quintessence discredited it. This section explains how a single convergence test generates both kinds of cosmological horizon. Light travels on a finite budget of conformal time, the integral of dt over a of t, where a of t is the scale factor. A horizon exists exactly when that integral converges at an endpoint. That single convergence test generates both kinds. Run the integral from the Big Bang at t equals 0 forward. If it converges, only a finite comoving sphere has had time to reach you. This is the particle horizon, the boundary of what could ever have been seen. Now run it from now to the end of time at t equals infinity or to recollapse at time t. If it converges, some events lie past a sphere. Your light will never cross. This is the event horizon, what can never be reached. Same integrand, opposite limit of integration. Convergence at that limit is the whole phenomenon. Radiation early makes the past converge. Vacuum energy late makes the future converge. This section explains why the cosmic microwave background survives as a thermal spectrum. One fact carries the chapter. Free expansion cannot deform a blackbody spectrum. Because cosmic redshift multiplies every photon frequency by the same factor, the ratio of the scale factor, at last scattering to the scale factor. Now, the Planck form is preserved exactly through decoupling. Only one parameter survives to slide, the temperature falling in proportion to 1 over the scale factor. So the photons that last scattered matter near 3000 Kelvin, when hydrogen recombined and the universe turned transparent, still wear a thermal spectrum today, redshifted to about 2.7 Kelvin. They are a fossil surface, streaming freely ever since. The inversion that carries the argument is this: equilibrium was needed to make the spectrum, never to keep it. The geometry inherits the bookkeeping equilibrium once did, and the sky becomes cosmology's cleanest observable. This section explains why the cosmic microwave background keeps its black body shape long after the photons stop interacting. Free expansion acts as a similarity transform on a black body spectrum. Dilute the photons, redshift each frequency by 1 over the scale factor, and every scale factor cancels except the one riding alongside temperature inside the Planck exponential. So the distribution that decouples from matter stays exactly blackbody, only cooler, with temperature proportional to 1 over the scale factor, only cooler, with temperature proportional to 1 over the scale factor, even after the photons stop interacting. That is the whole chapter in one move. Today's microwave sky at 2.725 Kelvin is a fossil Planck curve rather than a spectrum thermalized in the present. Its shape froze at last, scattering, and was merely rescaled by 15 billion years of expansion. The form survives only because post-decoupling scattering is elastic, meaning frequency preserving. Inelastic kicks would deform it, and the vast photon entropy ensures they do not. This section explains how a temperature hides inside the way any system fills its energy levels and how that single idea delivered the cosmic microwave background. A thermal bath writes its temperature into the occupation ratio of a system's energy levels. Read the ratio, recover the temperature. That is the whole section. The 2.7 Kelvin microwave background reached us first as a reading off the rotational populations of cyanogen in an interstellar cloud in 1941. The molecule was a thermometer whose 0.264 centimeter excitation matched a bath nobody had yet named, 24 years before Penzias and Wilson caught the same radiation as unexplained antenna noise. Here is the subtlety that carries the section. One intensity at one wavelength settles nothing, since the Rayleigh-Jeans tail fits any diluted spectrum equally well. Blackbody identity demands the wean fall off below 0.3 centimeters, which only the FIRA's instrument aboard COBE finally closed to a standing ovation. This section explains why one temperature law wins when two coupled populations are forced to share a single temperature. Two thermally coupled populations must share one temperature, yet expansion pulls them opposite ways. Free photons cool as 1 over A, while non-relativistic matter cools as 1 over A squared. Which law governs the mixture? Weinberg settles it by counting. In Chapter 2, one particle, one vote. Entropy per baryon is the tally, and photons outnumber baryons by about 10 to the 9th power. So the photon scaling, temperature proportional to 1 over A, carries almost exactly, and the Planck spectrum survives out of equilibrium untouched. The overwhelming majority of degrees of freedom dictates the shared intensive variable. This is the same reason a thermometer reads the bath, not itself. The boundary is self-generating. Invert the ratio, and matter's 1 over a squared would instead rule. This section explains recombination and last scattering the moment the universe turned transparent. Cool, a plasma, and the free electrons, the only thing photons scatter from, get captured into neutral hydrogen. Their density drops, the opacity collapses, and radiation streams free forever after. That decoupling surface is the microwave background, the universe photographed at the temperature where it turned transparent, about 3000 Kelvin, redshift of about 1090. The chapter's whole move is locating that surface. Equilibrium, the Saha formula, gives a first estimate that comes out too sharp. Real recombination lags behind it, bottlenecked at reaching the hydrogen ground state. And last scattering is a probability distribution over temperature rather than an instant spread across a range, narrow at about 10% only because the opacity falls so steeply. What you are seeing is the edge of a threshold, the gradual crossing itself. This section explains the dipole anisotropy, the single largest feature of the microwave sky. An isotropic photon bath, viewed from a moving frame, is no longer isotropic. The Doppler shift warms the sky ahead and cools it behind. In symbols, the temperature becomes T, divided by gamma times 1 plus beta. That single relativistic fact is the whole section. The largest departure from a uniform microwave background records the observer moving rather than the universe speaking. The bath defines an absolute rest frame. The thing special relativity forbids locally. An isotropic radiation field restores globally. The dipole simply reads off your velocity against it. 370 kilometers per second for the solar system, 627 for the local group. Expand in beta, and the same motion leaks a fainter, kinematic quadrupole. So, pure velocity already counterfeits real structure. This section explains the Sunyaev-Zeldovich effect, the way a galaxy cluster leaves its fingerprint on the cosmic microwave background. Photons falling through hot gas get kicked upward in energy. That is the whole effect. The CMB is a fixed blackbody bath. A galaxy clusters intracluster electrons, sitting at millions of Kelvin. Inverse. Compton scatter the photons crossing them, nudging each one toward higher frequency. The spectrum keeps its identity, but shears. Fewer photons below a crossover frequency, more above it, with the distortion changing sign at a fixed point set only by the scattering kinematics. Here's the part that should update you. This dip is redshift independent. It measures the electron pressure integrated along the line of sight, a surface brightness. A surface brightness holds constant with distance, where a flux would fall off, so a distant cluster dims no more than a near one. The same background. Read as a probe of whatever hot medium it traverses. This section explains why one map of the microwave sky, if the temperature field is Gaussian, compresses to a single sequence of numbers. Read one sky as a function on the sphere and decompose it in spherical harmonics. Rotational invariance forces the two-point average to diagonalize, so the entire cosmological content of the temperature field, if it is Gaussian, collapses to one sequence, the angular power spectrum, C of L. This is Fourier's move made under the rotation group SO3 rather than under translation. Isotropy diagonalizes the covariance, and the eigenvalues are everything. The section's real subject is the gap between what you want and what you have. What you want is an ensemble average over universes. What you have is one realization, seen from one vantage. The ergodic theorem equates the two, and one sky sampling sets an irreducible floor. The cosmic variance which goes as the square root of 2 over 2. A +1 and is worst at low L. Physics enters only afterward as the list of sources feeding the field. This section explains the early universe as cosmology's one computable regime and the single move that generates its predictions. Run the film backward and every complication burns off. Hot enough matter sits in thermal equilibrium, so its entire content is fixed by a single number, the temperature. This is cosmology's privileged regime, the one place you compute rather than observe, because equilibrium erases whatever the initial conditions once were. The chapter's single generative move is freeze out. A species decouples the instant its reaction rate drops below the expansion rate, that is, gamma less than h, and its co-moving abundance locks in as a fossil. One primitive, 3 fossils, the primordial helium of nucleosynthesis, the relic density of cold dark matter, and the baryon asymmetry that survives when matter narrowly outran antimatter. You predict the ash by reading the fire. This section explains the generative move behind Weinberg's 3rd chapter on the early universe. Reactions run faster than the universe expands, so at every instant the contents forget how they arrived. The whole plasma sits in thermal equilibrium fixed by a single number, its temperature. That is the generative move of Weinberg's Chapter 3. History collapses to one parameter. Entropy in a co-moving volume is conserved. The entropy density of T times the scale factor, A cubed, stays constant, so temperature falls as the inverse scale factor, and every density, pressure, and species population follows as a function of T alone. No ledger of initial conditions is needed. Equilibrium quotients away. the microstate detail and hands back a one-parameter trajectory. The early universe is memoryless. Knowing T is knowing everything until a reaction freezes out and the forgetting stops. This section explains how the energy, density, and pressure of a particle species are computed from its thermal distribution. A gas of particles at temperature T carries no independent thermodynamics. Every bulk quantity is a moment of one phase. Space occupation number, the Bose. Einstein or Fermi. Dirac distribution, fixed by T and the chemical potential. Energy density weights each mode by its energy, the square root of P squared plus M squared. Pressure weights it by P squared over 3E, the same integral, a different kernel. This is why the whole thermal history reduces to bookkeeping. Track which species stay coupled and sum their moments. Mass enters only through the dispersion relation, so both limits fall out of one formula. In the relativistic limit, where m is much less than t, the density is proportional to t to the fourth power. In the non-relativistic limit, it is Boltzmann, suppressed, going as e to the fourth power. When count the species, integrate. The universe's energy budget is a sum over occupied modes. This section resolves a surprise about free-streaming neutrinos. A free-streaming gas has no collisions to thermalize it, yet neutrinos keep a perfect thermal spectrum after decoupling. The Fermi-Dirac occupation depends on momentum only through two ratios, the ratio of momentum to temperature and the ratio of chemical potential to temperature. Cosmic expansion redshifts every momentum by the same factor, so momentum scales as 1 over the scale factor, A. So if you let the neutrino temperature scale as 1 over A, and each chemical potential scale as 1 over A in lockstep, both ratios stay frozen and the distribution never changes shape. This scaling is the unique redshift law under which a collisionless species masquerades as one still in equilibrium rather than the thermodynamics of an interacting fluid. Decoupling stops the interaction, not the thermal form. Expansion carries the spectrum rigidly downward. This section explains how the observed excess of matter over antimatter stops being a brute number and becomes something a theory must earn. Begin with a number that looks like an initial condition, eta, roughly 5 times 10 to the minus 10, the surviving excess of quarks over antiquarks. Sakharov turns this into a demand on any theory. Start from perfect particle and antiparticle symmetry. To end with net baryon number, you need 3 violations at once. First, a process that changes baryon number or lepton number. Second, a bias in its direction, meaning both C and CP are broken, because otherwise the forward and reverse rates cancel. Third, a departure from thermal equilibrium, because otherwise CPT forces equal masses, vanishing chemical potential, and any imbalance unmakes itself. The generative move is this. Manufacturing an asymmetry in a conserved quantity requires breaking the conservation, biasing the arrow, and escaping the equilibrium that would erase it. Drop any one condition and the universe stays symmetric. This section explains what the word cold means in cold dark matter and why that single property forces the shape of cosmic structure. Matter known only by its gravity, moving slowly enough that its thermal velocity smears out nothing. That is the whole content of cold. Set the pressure to 0 and the collision cross-section to 0. What remains is dust that only falls. Here is the generative move. An equation of state W approximately equal to 0 means gravity meets no restoring force, so density contrasts grow unopposed. Because the free streaming length is negligible, they grow at every scale. The smallest lumps form first and merge upward. Hierarchical, bottom-up structure is not an added assumption. It is what coldness forces. Now the contrast that reveals the structure. Make it hot instead, and free streaming erases small perturbations, giving top-down formation, and that is wrong. This section explains new inflation as slow roll made to last. Pin a scalar field high on a flat stretch of its potential, and its kinetic energy becomes negligible against the potential V of phi. Then, the pressure P is exponentially minus the energy density ρ, the equation of state of the vacuum itself. That single equality is the entire engine. A field that barely moves is the entire engine. A field that barely moves is indistinguishable from a cosmological constant, and a cosmological new inflation is just this slow roll made to last, the inflaton creeping downhill so gradually that the Hubble rate h falls only slightly, while enormous expansion accumulates. The two flatness conditions are precisely the demand that phi dot squared and phi double dot stay small. Meet them, and the exponential follows on its own. No phase transition, no nucleated bubbles required. This section explains how a single burst of exponential expansion before the hot Big Bang turns awkward initial conditions into generic ones. One exponential burst before the hot Big Bang converts every awkward initial condition into a generic one. A scalar field cresting a flat potential drives the scale factor to the minus, its second time derivative staying positive. Its second time derivative. It's staying positive while the expansion rate, the first derivative of the scale factor divided by the scale factor itself, stays nearly constant. Any curvature, measured as the size of the curvature term divided by the squared expansion rate, decays like the scale factor to the minus second power. So spatial flatness, the same factor of e to the n stretch swells one causally connected patch past the whole observable sky, which resolves the horizon puzzle, and it dilutes grand unified monopoles below detection. Three independent fine-tunings collapse into one dynamical number, the e-folding count n. The chapter's real payload is the byproduct. Inflation's quantum fluctuations seed the microwave background and large-scale structure. This is the lone prediction that, unlike the puzzles inflation was built to answer, observation could later confirm. This section explains three puzzles of the standard hot Big Bang and the chapter's quiet claim about what unites them. There are three separate embarrassments of the standard hot Big Bang, and the chapter's quiet claim is that they are one embarrassment wearing three masks. First, why is space so nearly flat when flatness is a repulsive fixed point? Any early deviation blows up, so a density parameter, omega close to 1 today, demands absurd fine-tuning at the start. Second, why do patches of sky that never shared a causal past sit at the same temperature? Third, why don't we drown in the magnetic monopoles that a grand unified early universe should mint? Each of these is an initial condition that standard expansion drives away from the observed value, so the value we see is a coincidence. The generative move is to suspect a dynamics that makes each one an attractor instead. That suspicion is inflation. This part explains how a single scalar field on a flat stretch of its own potential is the entire content of inflation, stripped of grand unification and bubble nucleation. The field is called the inflaton, and it obeys one equation of motion, the second time derivative of phi plus 3h times the first time derivative of phi plus v prime equals 0. This is an overdamped roll where the cosmic expansion rate h acts as friction on the field. When the potential V is flat enough that friction wins, phi crawls. Its kinetic energy stays negligible against V, so the equation of state locks to pressure approximately equal to minus the energy density, the vacuum's own signature, and space swells near, exponentially. The chapter's move is this reduction. What drives inflation is a slow roll, and flatness of the potential is the only ingredient. Everything downstream, the E-foldings, the CMB fluctuation spectrum, falls out of how slowly the field descends. This section explains why inflation needs no fine-tuned launch, and why once it starts, it never globally stops. Linde's move is to drop the demand for a special start and let the scalar field begin wherever it likes, large, generic, super Planckian in some patch, while a plane potential, 1/2 m squared phi squared, carries it. That patch inflates. Nothing else need be arranged. The eternal half is a drift diffusion race. Classical roll-down drains phi, while quantum fluctuations kick it back uphill by order. H each, Hubble time, where the kick beats the roll, that volume keeps inflating, and its exponential expansion outbreeds the regions that have exited. So inflation, once lit anywhere, never globally ends. It perpetually spawns pockets that reheat into ordinary cosmology, while the still inflating substrate grows without bound. This section explains how the general theory of small fluctuations gets built, and why the background symmetry does the organizing. Linearize Einstein's equations about the Robertson and Walker background, and the background's own symmetry becomes a selection rule on what you linearized. Because that background is spatially rotation invariant and translation invariant, the metric and matter fluctuations split into scalar, vector, and tensor pieces that evolve independently at first order. One coupled nonlinear system becomes 3 decoupled linear ones. General covariance leaves a residue. Some fluctuations are pure coordinate artifacts, killable by a gauge choice. Chapter 5 builds machinery rather than a phenomenon. What it builds is the symmetry block, diagonalized, gauge-fixed linear framework that every later chapter plugs into, the chapters on the cosmic microwave background and on structure formation. The generative primitive is this. The unbroken symmetry of a background dictates how its small perturbations are allowed to move. This section explains why cosmological perturbation theory splits into 3 independent channels. Linearize gravity plus matter around the isotropic, Robertson-Walker background, and the tangle Weinberg calls repulsively complicated collapses by a single move. A rotationally invariant operator cannot mix different representations of the rotation group, so the background's own symmetry forbids the coupling. Decompose every perturbation into scalars, divergenceless vectors, and traceless transverse tensors of helicity 0, 1, and 2. The field equations then block, diagonalize, each sector evolving on its own. This is Shor's lemma wearing a metric. Vectors decay as space expands. Scalars seed structure. Tensors are gravitational waves. Everything downstream, the cosmic microwave background anisotropy, galaxy formation, is bookkeeping inside these 3 decoupled channels, once the redundant gauge directions are quotiented away. This section explains how the field equations for cosmic structure become solvable. Start by splitting the metric into 2 pieces. A symmetric background, written g bar mu nu, plus a small deviation written h mu nu. So the full metric g mu nu equals g bar modity, because smallness kills the self-coupling nu. Keep only first order in that deviation. Einstein's ferociously nonlinear equations then collapse into a linear system for h mu nu. That linearity is the whole linear system for h mu nu. That linearity is the whole permission slip for the chapter can be solved mode by mode because smallness kills the self-coupling of gravity. The second move redeems the repulsively complicated result. The background carries a leftover symmetry, the spatial rotations and translations of Robertson and Walker. And that symmetry block diagonalizes h mu nu into three sectors: scalar, vector, and tensor. These sectors never talk to each other. This is the same primitive as normal modes about equilibrium. Linearize at a symmetric point and the symmetry group hands you decoupled, irreducible channels. Break the isotropy, and the sectors would recombine. This section explains why the Fourier decomposition of an infinitesimal perturbation splits cleanly into a deterministic operator and random coefficients. Translation symmetry is a diagonalization. Because the field equations are unchanged under spatial shifts, their eigenbasis is the plane waves, the exponential of I times the wave vector, k dotted with position x. And because the perturbations are infinitesimal, distinct wave numbers never couple. Every mode Q evolves by its own ordinary differential equations, depending only on the magnitude of equations, depending only on the magnitude of Q, never on the direction, so the dynamics is deterministic and mode by mode. All ignorance is quarantined into the initial amplitudes, alpha sub n of Q. They alone carry direction, randomness, and the memory that the universe is not rotationally symmetric. Demanding that the initial statistics be translation invariant, then forces the correlation of alpha with its complex conjugate to be proportional to a delta function of q minus q prime. One power spectrum per Magnus conjugate to be proportional to a delta function of q minus q prime. Deterministic operator, random coefficients. Symmetry sorts, which is which. This section explains what it means to choose a gauge in cosmological perturbation theory. Split space-time into a smooth background, plus a tiny perturbation, and you have made a choice nature never made. The split depends on how you lay coordinates over the background. An infinitesimal coordinate shift, x becomes x plus epsilon, repaints part of the perturbation, even conjuring fluctuations out of a perfectly homogeneous universe. So the perturbation variables are partly fiction variables are partly fiction. Only combinations invariant under that shift carry physics. Choosing a gauge is fixing that redundancy, imposing conditions, synchronous or Newtonian, that exhaust the coordinate freedom until each variable is pinned. This is the same redundant description move as the vector potential in electromagnetism. The freedom is genuine, and the physics lives in whatever survives it. This section explains why a cosmological prediction can survive an epoch of physics nobody understands. A conserved quantity is a bridge across an interval you cannot see into. Between inflation and observation sit reheating and dark matter decoupling. Physics, whose details Weinberg flatly admits nobody knows. The prediction survives anyway. A mode whose physical wave number, q over a, drops below the expansion rate. H is outside the horizon. No causal process spans it, so the curvature perturbation r and its cousin zeta sits frozen. The prediction is carried by the adiabatic solution. Weinberg's theorem guarantees one exists, whatever the universe contains, holding r constant outside the horizon regardless of the unknown constituents. Ignorance of the middle costs nothing when a quantity refuses to change through it. This section explains how a given primordial spectrum evolves once each mode enters the horizon. Given the primordial spectrum, one comparison decides a mode's entire history. Did its wavelength cross inside the horizon while radiation still dominated, or after matter took over? That single clock race, horizon entry against radiation-matter equality bifurcates the chapter. Short modes enter early, oscillate as an acoustic fluid, and damp. Long modes enter early, oscillate as an acoustic fluid, and damp. The tractability trick is hydrodynamic. Before recombination, Thomson scattering chains photons to baryons so tightly that the four species collapse to one fluid, and the kinetic theory of section 6.1 becomes fluid equations solvable by hand. Solve each regime, interpolate between them, and you have the transfer function, the linear map carrying inflation's initial conditions to everything. Chapter 7 reads off the microwave sky. This section explains how the entire history of primordial density ripples reduces to a single comparison. Small primordial density ripples evolve, and the whole of their history collapses onto one comparison, a mode's co-moving wavelength against the horizon at the moment it re-enters it. Linear theory decouples every Fourier mode, so each Wava number k evolves alone. The horizon acts as a moving comb that sorts them. The sorting turns on one question. When the mode re-enters, which era is it? A mode that enters during radiation domination has a short wavelength, and their pressure resists gravity, so the mode oscillates and gets suppressed. A mode that enters during matter domination has a long wavelength, and it grows freely. Everything else is bookkeeping around that single case. Split, the two analytic regimes, the interpolation between them, and the tensor modes. The chapter's payload is the transfer function, the map from the primordial spectrum to what chapters 7 and 8 confront against the sky. This section explains why scalar perturbations are treated with kinetic theory rather than as a fluid. A fluid remembers only its first two moments, density and velocity. Radiation that no longer collides remembers everything. That is the whole move here. Track each species' full phase. Space distribution evolved by its own Boltzmann equation rather than collapse it to pressure and flow. For cold, dark matter, the two descriptions coincide. For photons and neutrinos, they cannot. Free-streaming pumps power into arbitrarily high angular multipoles that a fluid throws away. The intensity matrix, written Jij, carries exactly that angular structure, and off the diagonal, it carries polarization. The line of sight solution then folds the whole hierarchy back into a single integral of a source along the photon path. That integral is the exact substrate, the hydrodynamic sections that follow only approximate. This section explains the hydrodynamic limit for scalar perturbations, and why fast collisions let a full kinetic description collapse to just 3 numbers. Fast collisions erase memory of a distribution's shape. When photons scatter off free electrons quickly enough, as they do before recombination, the photon gas is dragged into local thermal equilibrium with the baryonic plasma, and its full kinetic description collapses to 3 numbers: density, bulk velocity, and pressure. That is the entire move of the hydrodynamic limit, an analytically hopeless Boltzmann hierarchy over 4 species: cold, dark matter, baryons, photons, and neutrinos, becomes closed fluid equations coupled through a single gravitational potential, cheap enough to solve by hand. The price is paid at the boundary where it fails. Mere recombination scattering slows, photons begin to stream freely, and the fluid picture must be repaired for damping rather than trusted. This section explains why a scalar perturbation stretched past the horizon stops evolving, and why that matters for the rest of the book. A perturbation stretched past the horizon has no causal clock. Nothing propagates across it, so it cannot dynamically evolve. What looks like change is only the background. FRW metric, rescaling itself beneath a mode that rides it as pure gauge. So the curvature amplitude R at wave number Q freezes while the wavelength stays superhorizon. This is the same Goldstone move. Weinberg flags in a footnote, a long wavelength excitation becoming a free, conserved mode. That freezing is the section's whole job in the book's arc. It carries inflation's initial condition, set in Chapter 10, intact across the opaque plasma epoch to horizon re-entry. So you never need the intervening physics to know what re-enters. This section explains how the short wavelength scalar perturbations are solved and why they split cleanly into two kinds of behavior. The strategy is the same asymptotic matching used for the long wavelength twin, but here horizon crossing happens while radiation still dominates, and once a mode is inside the horizon, a new fast clock appears. That splits the coupled photon, baryon, and dark matter system by rate. The slow modes track the background. Their time derivatives are of order h, and the gravitational potential is merely decaying. The fast modes are rapidly oscillating sound waves. Their physical wave number is q over a. Their speed is 1 over the square root of 3 times 1 plus r. And they are silk damped by photon diffusion. Each sector solves on its own. Then, the deep inside horizon solution patches onto the early radiation-dominated one across their overlap window. Here is the primitive. When horizon entry makes one timescale fast, the solution space factors into a slow adiabatic sector and a fast oscillatory one. This is a two-timing separation, each half analytically tractable, married at the seam. This section explains how section 6.5 bridges the two solvable regimes of scalar perturbation, evolution. Two solvable regimes bracket a gap. The wavelengths that fall through the gap are the ones entering the horizon near matter radiation equality, precisely those that set the first acoustic peak at the multipole L around 200. Section 6.5 closes that gap by refusing to solve the messy middle directly. Everything the evolution can depend on collapses onto a single dimensionless number, kappa, the wave number measured against the scale at equality. This works because the perturbation ratios are themselves dimensionless and independent of how the coordinates are normalized, so nothing else is admissible as a variable. From there, the recipe is simple. Solve the single, exactly tractable limit, 0 baryon mass and no damping. Seat the two analytic ends onto that solution. The whole map, from the primordial amplitude to the evolved amplitude, then becomes a transfer function of kappa, which the later chapters consume as a black box. The method is forced similarity. Because everything reduces to one variable, the two analytic ends must join through it, and the messy middle is reached by that similarity constraint alone, with no brute numerical integration required. This section explains why the tensor mode of a metric perturbation is the cleanest window onto the early universe. Begin by sorting every metric perturbation by how it transforms under spatial rotations. One piece, the transverse traceless part, spin 2, carrying two polarizations, refuses to mix with the rest. That decoupling is the whole content. To first order the tensor mode, neither source's density and velocity, nor is source's density and velocity. Because of this, Einstein's equations hand it back a single wave equation, formally the equation of a massless scalar minimally coupled to the expanding background. Gravitational radiation therefore propagates freely through the cosmic fluid, redshifting and damping with the expansion, but never generated by it. Its spectrum reads the primordial initial conditions almost unmediated. It is the cleanest channel from inflation to the sky, whereas the scalar sector is continuously reprocessed by the matter it lives in. This section explains why the microwave sky is read as a spectrum rather than a picture. The cosmic microwave background arrives at nearly the same temperature from every direction. The anisotropies are the departures from that uniform temperature, 1 part in 10 to the 5th power, and they are the entire signal. Each direction's tiny temperature deviation is the imprint of a density perturbation on the surface where light last scattered. So the sky is not a picture of space, but of a single instant, recombination, projected onto a sphere. Decompose the map into spherical harmonics and you get a power spectrum, the strength of the fluctuation as a function of angular scale. The chapter's move is that reduction. A two-dimensional sky becomes a curve whose shape is the cosmological parameters themselves, not a portrait of structure. This section explains how the sky's temperature map is the previous chapter's fluctuation field, projected onto the sphere we observe. The temperature map of the sky is nothing new. It is the fluctuation field of the previous chapter, projected. Every perturbation Weinberg evolved, density, velocity, potential, and gravitational waves, sits at the last scattering surface. A single line of sight integral collapses. That three-dimensional field along each direction, and hat integral collapses that three-dimensional field along each direction, a nat into one number, the fractional. The chapter's whole labor is turning the evolution into an observable. You expand the map in spherical harmonics, and because the universe is statistically isotropic, the entire content lives in the angular power spectrum, C sub L, not in the particular map. Scalar and tensor modes project through the same integral, but carry distinct signatures. That seam is what the next section, on polarization, prees open to tell them apart. This section explains where every temperature anisotropy formula in the chapter comes from. What you see in a direction is the photon's whole history projected onto a single number. Weinberg's opening move is exact. The fractional temperature fluctuation in a direction, n hat, equals today's photon density matrix value, rewritten as a line-of-sight integral, running back to before recombination. Each moment along the path contributes its source function, its density perturbation, its velocity, and its metric potentials. Each of these is weighted by the visibility factor, the exponential of minus, the integral of the collision rate, omega phi over time. That factor is the chance the photon scattered then, rather than earlier. That single integral is the generative object, the split into an early piece and an integrated Sachs-Wolf piece, and later the multipole coefficients, C sub L, are only rearrangements of it. Fix the sources and the geometry, and every anisotropy formula in the chapter falls out of this one projection. This section walks through a single transform that carries the whole scalar story. The temperature field left at last scattering, a function of spatial wave number q, is pushed through a spherical Bessel kernel into the angular multipoles you actually observe, the CL coefficients. The kernel, JL of q times RL, is pure geometry. It maps a wavelength on the last scattering sphere onto the angle that wavelength subtends today, L approximately equal to q times RL. All the physics collapses into two form factors evaluated at recombination. The first is the intrinsic temperature plus potential piece, the Sachs-Wolf term. The second is the baryon velocity piece, the Doppler term. Their acoustic oscillations in Q resurface as the peaks in L. Silk and Landau damping wipes out the smallest scales. The scalar spectrum is that projection, and the fit to W map is where the cosmological parameters fall out. This section explains how the tensor modes of the temperature multipole coefficients arise from the same machinery as every other mode in Chapter 7. One line of sight integral runs the whole of Chapter 7, and each mode type merely hands it a different source. Section 7.2 fed it the scalar potential. Here the source is d.ij, the time derivative of the transverse traceless metric, perturbation, a primordial gravitational wave shearing photons as they stream across it, one substitution, wave shearing photons as they stream across it, the same CL machinery, one substitution. The payoff lives in that substitution's physics. dq stays frozen outside the horizon, then decays and oscillates once it re-enters. So tensor modes imprint only at large angular scales and vanish at high L with no acoustic peaks. That decay is why the tensor signal is inflation's clean fingerprint. Its amplitude. The tensor signal is inflation's clean fingerprint. This section explains the geometry of how the microwave background becomes polarized. Scattering off free electrons at recombination linearly polarizes the microwave background, and the geometry of that polarization is the whole point. At each point on the sky, the polarization is a director, a headless axis left unchanged by a half turn. The Stokes combination, Q plus or minus IU, betrays this. Under a rotation by angle psi, it acquires a phase equal to e to the power, plus or minus 2 I psi. That makes it weight 2, where the temperature fluctuation carries weight 0. From that one exponent, everything downstream follows. A spin 2 field on the sphere demands spin-weighted harmonics. The ordinary spherical ones that temperature uses no longer suffice, and the eventual split by parity into E modes and B modes is already latent in the same exponent. Read the weight, and you predict the apparatus. This section explains how gravity grows cosmic structure out of tiny fluctuations. Gravity is a self-amplifying instability. A region denser than average gravitates harder, expands slower, and grows denser still. That single feedback loop makes every galaxy. The chapter carries the linear fluctuation field. The previous chapters built forward past recombination. There, cold dark matter overdensities grow only in proportion to the scale factor, with the expansion bleeding off the collapse. The generative move is Birkhoff's theorem. A uniform overdense sphere ignores everything outside it and evolves as its own closed. Robertson-Walker universe, turning around, collapsing, and virializing while the cosmos around it keeps expanding. Baryons merely fall into the wells, the dark matter already dug, then cool. So you can predict the rest. Structure is wherever the instability crossed from, linear amplification into a detached sub-universe. This section explains how gravity turns the faint, primordial ripples of the early universe into the galaxies and clusters we actually observe. Start from one idea. Gravity is an amplifier of contrast. The chapter takes the primordial fluctuations, the quantity R, sub Q, 0, handed down by inflation, and read directly off the microwave sky, and runs them forward through that amplifier into real structure. The single thesis is this. Once matter dominates the energy budget, every overdensity self-attracts, while the ongoing cosmic expansion throttles the gain. So the contrast grows as a power of the scale factor. The density contrast delta is proportional to the scale factor, A, which itself grows as the time t to the 2/3 power. This growth is slow, linear, and reversible in description. That gentle regime ends the moment the contrast delta reaches order. 1. From there, self-gravity outruns the expansion. Collapse becomes runaway and nonlinear. Halos virialize into stable bound objects, and the baryons finally cool and sink inside them. In Weinberg's arc, then, structure is primordial noise integrated through a gravitational amplifier, an amplifier whose gain the universe's own stretching keeps in check. This section explains what happens to linear perturbations once recombination is over. Once recombination frees the baryons, they stop being pressure locked to the photons and become just another dust, pressureless cold matter. Dust under gravity carries no length scale, so the linear growth equation separates. The density contrast factorizes into two pieces, a wave and number factor frozen at last scattering, times one universal growth function, f of t, that last scattering, times one universal growth function, f of t, that lifts every mode identically stay. The spatial pattern is written once, at decoupling. Afterward, time only rescales it. Baryon and dark matter contrasts, wildly different at decoupling, converge to a common matter contrast, delta M. That separation is the whole gift. Today's observed clustering reads straight back to the primordial curvature, perturbation R, with all cosmology confined to f of t. Scale freedom is only approximate. Restore baryon pressure, and a smallest wavelength returns, breaking it, as section 8.3 shows. This section explains why nonlinear collapse gets replaced by an exactly solvable proxy, and where the universal number 1.686 comes from. Collapse resists direct solution. The nonlinear regime lives in computer simulations, so the chapter swaps the intractable problem for an exactly solvable proxy. Peebles's move is this. A uniform overdense sphere is itself a closed Robertson. Walker universe by Birkhoff's theorem, so it runs its own Friedmann equation. It expands, turns around, and recollapses with no reference to anything outside. The payoff is a universal number. Linear theory, extrapolated to the collapse instant, always reads 1.686, whatever the fluctuation strength. That fixed threshold becomes a knife on the Gaussian field. Press and Schechter count halos of each mass as the fraction of the linear density exceeding 1.686. Intractable dynamics re-imported through one scale, free constant. This section explains how baryonic matter collapses into structure. Gravity carries no length scale. Pressure does, and that single asymmetry generates the entire section. Cold, dark matter, being pressureless, collapses on every scale. Baryons resist through their sound speed, which turns any density bump into a race between infall and pressure smoothing. The race fixes one number, the gene's mass. Sound speed times free. Fall time sets a critical wavelength, and only clumps heavier than it can drag baryons into the dark matter wells, already deepening around them, roughly 10 to the 5th power. Solar masses of gas. Below that mass, the well stays dark and baryon. Structure is thus a filter. Dark matter writes the potential landscape, and pressure decides which valleys the gas is permitted to fall into. This section explains how gravitational lensing is a single map read-off different mass distributions. Mass bends light, so any foreground mass becomes a map from source angle to image angle. That map is the lens equation, and every phenomenon in the chapter is that one map read off a different mass profile. Where the map falls, its Jacobian degenerates. Two images collapse into one along an Einstein ring, and the brightness diverges. Surface brightness is conserved, but the solid angle inflates. Paths of unequal length give a measurable time delay. Point mass, isothermal sphere, smooth, cosmic web, cosmic string. The same equation, only a richer lens each time. Weinberg's move is to invert it. The distortions encode the deflecting mass, which is dark matter, and the distances along the line of sight, turning lensing into cosmology's ruler and its scale. This section explains gravitational lensing as a single, reversible move. Mass bends the null geodesics that graze it, so a foreground body acts as a lens. It remaps where a background source appears against where it truly sits. The whole chapter is one gesture. Write that remapping as an equation, with the deflection fixed by the enclosed mass and the geometry fixed by the angular diameter distances, and then read it backwards. Read forwards, one source can split into several images. Inverted, the image pattern weighs the lens, including mass that shines no light. And since the images ride paths of different length, the delay between them fixes an absolute distance, and so the Hubble constant, h0. Gravitational lensing is therefore a coordinate map on the sky whose inverse is at once a mass and a scale. This section explains the lens equation for a single point mass. A point mass bends any passing ray by a fixed angle. Because of that, the direction you see a source in is set by a self-consistency condition. The observed angle equals the true angle plus a deflection, and that deflection itself depends on the observed angle. That implicit equation is a fixed point problem in angle, and it is the whole of section 9.1. Generically, it has two roots, so there are two images straddling the lens. The deflection sets one scale, the Einstein radius, written beta E, built from the three Earth to lens to source angular diameter distances. When source, lens, and Earth align perfectly, the discrete roots dissolve into a continuous rotational orbit. The two images smear into the Einstein ring, a broken symmetry momentarily restored. This section explains how gravitational lensing brightens the source and how one quantity splits into two observational regimes. A lens adds no photons. It conserves surface brightness, meaning flux per solid angle is invariant along a ray bundle. So the only way bending light can brighten a source is by making it subtend more sky. Magnification is exactly the ratio of image solid angle to source solid angle, the Jacobian of the lens map. That single quantity forks by what you can resolve. Strong lensing resolves the separate images, and the Jacobian diverges where those images merge. The Einstein ring is that caustic limit. Microlensing is the same map when the lens and the source lie too close to split apart. You see only their summed flux, so a stellar mass drifting across a star reads as a symmetric brightening in time. This section explains what happens to a gravitational lens when the deflector is a real galaxy with an extended halo rather than a single point of mass. A real galaxy has spatial extent. Its halo spreads across a region, so the deflection now depends on how that mass is distributed. Model the halo as an isothermal sphere, its pressure fixed by the stellar velocity dispersion, the mean squared velocity of the stars. In this model, the density falls as 1 over r squared, so the enclosed mass grows linearly in proportion to r. The decisive consequence follows. A ray bends by an angle equal to 4 pi times the mean squared velocity, and that angle is independent of the impact parameter. Every ray, whether it passes near the center or far from it, turns through the same angle. The 1 over b falloff of the point mass is gone. That flat deflection linearizes the lens equation. It splits the source into two images, separated by 8 pi times the mean squared velocity, and it turns the lensing counts, the number of lenses as a function of redshift z, into a clean probe of omega lambda. This section explains how a gravitationally lensed source becomes a cosmic clock. A multiply image source hands you a clock. The same brightness fluctuation reaches Earth at different times in each lensed image, because each image's light rode a different route past the lens. Two contributions set the offset. The first is a geometric delay. The bent path is simply longer, computed as a geodesic triangle in the Robertson-Walker metric. The second, folded in through the footnote, is a gravitational delay, the Shapiro delay, from time running slow in the lens's potential. Here is the primitive worth carrying. The differential arrival time is a directly measured duration, while the geometry fixes the matching length. Their ratio is an absolute distance, and hence the Hubble constant with no distance ladder underneath. This is Refstall's point, made in 1964. This section explains how weak lensing turns a signal no single galaxy can show into a measurement of all the mass along the line of sight. Every galaxy's shape carries a distortion too faint to read off any single image. The shear from foreground mass is a percent-level stretch buried under the galaxy's own intrinsic ellipticity. The generative move is this. What is undetectable per object becomes measurable in the correlation. Average the ellipticity over many galaxies and the random intrinsic shapes cancel, leaving only the coherent shear imprinted by the intervening density field. So this part turns the chapter's single-lens formalism into a statistical instrument. The shear two-point function reads out the matter power spectrum, P of k, directly, weighing all mass along the line of sight without assuming that light traces it. The signal sits beneath the noise floor, recovered by summing over an ensemble. This section explains what a cosmic string is and why its gravity gives it away. A cosmic string is where a symmetry broke everywhere, but along a line, a one-dimensional scar that the early universe's phase transition left frozen into space-time. Its gravitational signature carries the surprise. The deflection it gives a passing light ray depends on neither the ray's distance nor the string's distance, only on their mutual angle. That flatness betrays the geometry. A string is codimension too, so its exterior space-time is conical, flat, yet missing a wedge. Every ray crossing the deficit bends alike, splitting a source behind it into two images. Weinberg's note is deflationary. This clean signature is nearly our only handle, and the lone 2003 candidate dissolved into two colliding galaxies. This section explains how inflation turns quantum uncertainty into the seed of cosmic structure. Stretch the vacuum until its jitter can no longer oscillate, and quantum uncertainty freezes into a classical random field. That is the entire chapter. Each Fourier mode of the inflaton oscillates as a harmonic vacuum until inflation carries its wavelength past the Hubble horizon, where its frequency drops below the expansion rate. The mode then stops oscillating, and its amplitude freezes as a conserved curvature perturbation. The vacuum's zero-point spread becomes one definite classical draw per mode. Here, the primordial spectrum is born, the seed that the rest of the book processes into microwave background, anisotropies in galaxies. Horizon exit is the operator promoting microscopic quantum indeterminacy to macroscopic cosmic structure. This part explains where the galaxies come from. Quantum jitter, frozen and stretched to the size of the sky. A single scalar field called the inflaton carries unavoidable vacuum fluctuations. Exponential expansion drags each mode's wavelength past the horizon, and once a mode is superhorizon, its time derivative is friction, damped to nothing, so the amplitude freezes into a classical, conserved curvature perturbation, written R. The chapter's whole job is to convert this, to compute the primordial spectrum that chapters 5 through 9 simply assumed as initial data. The structural move is generative, Any light field in de Sitter space inherits a nearly scale invariant spectrum because every mode meets the same horizon, crossing the same way. The origin of cosmic structure is a quantum to classical freeze-out. This part explains how the seeds of cosmic structure emerge from quantum fluctuations during inflation. A quantum field, living in an exponentially expanding spacetime, once decomposed into co-moving Fourier modes, is just a bath of harmonic oscillators whose physical wavelengths stretch along with the expansion. While a mode sits deep inside the Hubble horizon, it oscillates and rests in its ground state, the Bunch and Davies vacuum. As inflation drags that mode's wavelength past the horizon, the oscillator freezes. Its zero-point jitter stops oscillating and survives instead as a classical amplitude. Weinberg's move is to carry that amplitude in the curvature perturbation, written R, which is conserved outside the horizon, so the frozen spectrum crosses the entire unknown reheating era untouched and re-enters as the seed of structure. Cosmic structure is magnified vacuum noise. This section explains how gravitational waves are generated during inflation, spacetime's own shape ripples. The transverse traceless part of the metric perturbation, the two polarizations of a gravitational wave, obeys during inflation exactly the equation of a massless scalar in de Sitter space. So each mode is amplified and frozen the same way. Quantum vacuum fluctuations stretched past the horizon, their amplitude set by the Hubble rate. H at horizon crossing and nothing else. That is the whole point of the section. Tensors carry no imprint of the inflatant's potential shape and no coupling to matter. Their spectrum reads off the inflatant's potential shape. The scalar case is the messier sibling. Detect the primordial B mode they leave, and you have measured H, the cleanest observable inflation offers. This section explains how fluctuations during inflation get computed once exact solutions are no longer available. Exact solutions die for a general potential. The slow roll approximation is the single move that revives them. Assume the Hubble rate H barely changes across the window where a mode crosses the horizon, the window where Q over H is approximately 1. This is legitimate because the frozen amplitude depends only on the fields at crossing, never on the start or end of inflitude, depends only on the fields at crossing, never on the start or end of enthalphin. Then, the exact Molchanov and Sasaki equation collapses to Bessel form of order nu equals 1/2 plus 2 epsilon plus delta. Its solution is pinned by the deep subhorizon initial condition, and it freezes once outside. The frozen amplitude inherits a clean power law. R sub q scales as q to the power minus 3, halves minus 2 epsilon minus delta. The near scale invariant tilt is just the slow roll parameters epsilon and delta read off at crossing. Horizon crossing is the whole calculation. This section explains why the observed shape of primordial fluctuations does not pin down the number of fields that inflated. The observed signature of primordial fluctuations reads like the fingerprint of a single inflaton. It is Gaussian, adiabatic, scale invariant, and weak. The move here is to show that this signature survives arbitrarily many fields. The one-field premise, assumption 1, is what bought adiabaticity. Weinberg swaps it for thermalization at reheating, call it assumption 1 star, where local equilibrium with vanishing chemical potentials erases which field carried the energy. What replaces the lone scalar is geometry. The n fields are coordinates on a curved manifold with a field metric, gamma nm carrying its own affine connection and Riemann curvature, a nonlinear sigma model. The statistics are the invariant. The field count is a choice of chart. and the data cannot read the chart.